Michio Kaku reveals insight into a surprising revelation. The James Webb Space Telescope has recognized a disturbing signal transmitting from the Andromeda cosmic system for north of a century. How we might interpret Andromeda was generally terrestrial, but at this point, outfitted with the James Webb Space Telescope, our viewpoints are decisively shifting. This new information has sent shockwaves through established researchers. However, what does this stunning revelation tell us? And for what reason is it creating such a ruckus among space experts? Join us as we delve into the subtleties of this disclosure and explore how it affects how we might interpret our adjoining universe. Before we dig into the details of the disturbing sign, it's significant to see some context about the Andromeda world. Generally, the Andromeda universe was the first hint that our universe extends beyond the Milky Way. This revelation shifted our understanding, highlighting that we may just be a small piece of a vast universe. Initially, the Milky Way was seen as the whole of the universe. Early cosmologists, using limited technology, could not separate the Milky Way into individual stars. This changed with Galileo Galilei in the 17th century. Using a telescope, he found that the Milky Way was comprised of numerous stars. This finding began to challenge the idea that the Milky Way was the universe's only world. The real game-changer came with Edwin Hubble during the 1920s. Using the Hubble telescope, he noticed distant objects beyond the Milky Way, identifying these as separate galaxies, expanding our view of the universe. One of these galaxies was Andromeda, also known as M31. Its observation dates back to the Persian astronomer Abd al-Rahman al-Sufi in the 10th century, who noted it without the aid of telescopic technology. By the 20th century, technological advancements allowed astronomers to explore further. They understood that Andromeda was an indistinct cloud with a vast universe of stars, similar to our Milky Way but located around 2.537 million light-years away. The study of Andromeda has evolved significantly since then. Observations have shifted from ground-based telescopes to space observatories like the Hubble and presently the James Webb Space Telescope. Each new instrument has brought us closer to understanding Andromeda's real essence. Deciphering Andromeda's design and organization helps astronomers delve deeper into the universe. It serves as a benchmark for our Milky Way, offering insights into system development and evolution. The relationship between the two galaxies is crucial for understanding the fate of our Milky Way, especially since they are expected to collide in around 4 billion years. Recently, the James Webb Telescope has received a disturbing signal from the Andromeda Galaxy. But what does the latest signal tell us? The James Webb Telescope has brought new insights. This exceptional instrument, infinitely better than its predecessors, has captured data from Andromeda that challenges previous understandings. The telescope's robust sensors have detected unusual activity in Andromeda's center, varying significantly from past observations. This has intrigued scientists worldwide. The signal suggests vital processes are happening inside the galaxy, potentially linked with its truly massive black hole or previously concealed anomalies. One key finding is the change in Andromeda's mass. Earlier estimates set Andromeda as significantly larger than the Milky Way. However, new data suggests this gap may not be as vast as previously thought. Updated measurements indicate that Andromeda and the Milky Way are more comparable in size, reshaping how we might interpret our own galaxy's place. Additionally, the James Webb Telescope has provided clear images and spectra from Andromeda. These have revealed new star formations and chemical compositions within the galaxy. Such details are crucial for understanding how galaxies evolve and what conditions could lead to life. Another significant discovery involves Andromeda's active cosmic core. The data shows that the black hole at the center is more active than previously believed. This activity affects the surrounding region and may influence the galaxy's overall structure and future. The telescope's findings also touch on the mysterious dark matter. By studying the gravitational effects on Andromeda's stars, researchers can better understand how dark matter is distributed throughout the universe. This is essential to addressing one of cosmology's biggest mysteries. What is dark matter, and how does it affect the universe? These new discoveries by the James Webb Telescope have led to various studies. Scientists worldwide are analyzing the data to uncover more about Andromeda's secrets. Each finding helps piece together the galaxy's history and future, providing a clearer understanding of the universe's workings. Andromeda, our nearest cosmic neighbor, has a variety of unique features that interest astronomers and set it apart from other galaxies. Firstly, Andromeda's size is significant. While estimates have changed, recent data suggest it spans around 220,000 light-years in diameter, making it one of the largest galaxies in the local group. Much larger than the Milky Way, its immense size contributes to its mass, holding an estimated 1 trillion stars, surpassing the number in our own galaxy. Andromeda's structure is another point of interest. It has a typical spiral shape but with a bulge. The galaxy contains a bulging center surrounded by rings of dust and gas, which are sites of active star formation. These features indicate a vibrant galaxy with ongoing processes that shape its appearance and evolution. The core of Andromeda is particularly interesting due to the presence of a double-capped outflow, suggesting it may harbor a very large black hole. This is similar to the Milky Way, but the nature and activity level of Andromeda's black hole provide valuable information for understanding these space objects. Additionally, Andromeda is surrounded by a corona of celestial material extending hundreds of thousands of light-years. This corona is composed of stars, planetary nebulae, and globular clusters, providing evidence of the galaxy's complex evolution and history. The globular clusters, in particular, are of significant interest, with more than 460 identified. They offer insights into the early stages of the universe's development and the dynamics of star clusters. Another unique aspect of Andromeda is its satellite galaxies. More than 20 smaller galaxies orbit Andromeda, some of which are being tidally stripped of their stars and gas, contributing to Andromeda's growth. This process, known as galactic cannibalism, highlights the aggressive nature of galaxy evolution and provides a live example of how galaxies grow and interact over time. But how is the Andromeda Galaxy evolving, and what does its future hold? The evolution and future of the Andromeda Galaxy are subjects of significant interest and research in astronomy. One significant aspect of Andromeda's evolution is its potential transition from a spiral to a ring galaxy. Observations suggest changes in the pattern could lead to this rare structure. Ring galaxies are rare and form under specific conditions, often after a collision or near miss with another galaxy. If Andromeda is evolving into this structure, it indicates a history involving interactions with other galaxies. Andromeda's future is closely tied to its interaction with the Milky Way. Estimates predict that in around 4 billion years, Andromeda and the Milky Way will collide and merge. This event, while seemingly catastrophic, is a natural part of cosmic evolution. The collision will not involve direct collisions between stars due to the vast distances between them. However, the gravitational forces will reshape both galaxies. During the merger, gas and dust from both galaxies will interact, leading to new bursts of star formation. This burst of celestial creation will illuminate the merging galaxies, creating a unique and spectacular cosmic event. The collision will ultimately result in a single elliptical galaxy, a process common in the universe's history but unique in human terms. Given that our direct involvement in these events is highly unlikely, the very large black holes at the centers of both galaxies are also expected to merge. This event could result in significant emissions of radiation as matter is absorbed by the newly formed black hole. Focusing on this process provides insights into the life cycles of galaxies and the role of black holes in their evolution. So, what does the future of Andromeda and its expected merger with the Milky Way mean for the fate of our local planetary group? While it is unlikely that the planetary group will be destroyed, its position and conditions could significantly change. This includes potential shifts in orbit or even expulsion from the newly formed system. Understanding these processes helps scientists predict the outcomes of similar events elsewhere and provides context for the possible fate of our own planet. The study of Andromeda's evolution and future is about understanding the forces at play and the inevitable evolution of galaxies over billions of years. The expected merger between our galaxy and Andromeda raises significant questions about its impact on Earth's environment. It is essential to understand that the vast distances between stars mean that actual star-on-star impacts are unlikely. However, the gravitational effects of such a merger would be significant. The merger could disrupt the stable orbits of stars and potentially send many of them, including our Sun, into new trajectories. This change in position could have significant implications for Earth's climate. If Earth's distance from the Sun changes significantly, it could either heat up or cool down, depending on the direction of the change. A warmer climate could lead to melting ice caps and rising sea levels, while a cooler climate could trigger a new ice age. Additionally, the merger could lead to increased radiation reaching Earth. As the Milky Way and Andromeda's black holes approach each other, their interactions could accelerate particles to high energies, increasing the amount of cosmic radiation entering Earth's atmosphere. This increase in radiation could have detrimental effects on Earth's ecosystems, potentially leading to increased mutation rates in organisms and impacting biodiversity. Changes in Earth's orbit or axis could also disrupt the distribution of ecosystems across the globe. Species adapted to specific climate zones could find their habitats unsuitable, leading to shifts in biodiversity and ecosystem structures. Some species could thrive under these new conditions, while others could face extinction. Furthermore, the merger may trigger new star formation as gas clouds from both galaxies collide and compress. If this star formation occurs near the planetary system, the radiation from these new stars could also affect Earth's environment, further influencing climate and life. However, it is essential to note that these events are projected to occur billions of years in the future. Human life as we know it may have evolved significantly by then, or our species could inhabit different parts of the galaxy or universe. The findings from the Andromeda Galaxy have significant implications for understanding our own galaxy and its future. The comparison between Andromeda and the Milky Way helps astronomers better understand the structure and evolution of spiral galaxies. Observing Andromeda's dynamics, such as its spiral arms and the activity around its supermassive black hole, provides a reference point to focus on similar features within the Milky Way. This comparative study refines our models of cosmic dynamics and evolution. Moreover, the discovery of Andromeda's size and mass has direct implications for how we interpret the Milky Way. Initial assumptions set Andromeda as significantly larger than the Milky Way. However, recent data suggest that the two galaxies may be more comparable in size than previously thought. This challenges our perspective on the Milky Way's position in the local group of galaxies and its gravitational influence. Although the Milky Way is currently a barred spiral galaxy, interactions with neighboring galaxies, especially Andromeda, could change its structure. Understanding Andromeda's evolution provides clues about the events that lead to such massive changes in galaxy morphology. By focusing on Andromeda's current status and predicting its future trajectory, astronomers can simulate the effects on the Milky Way. This includes changes in star formation, the distribution of gas and dust, and the dynamics of both galactic cores. The field of astronomy has experienced significant changes thanks to technological advancements. From the earliest telescopes to the sophisticated observatories of today, each step forward has expanded our understanding of space. The journey began with the invention of the telescope in the early 17th century. This simple device, consisting of lenses inside a tube, allowed astronomers to observe the moons of Jupiter and the phases of Venus. Over time, so did the complexity and power of telescopes. The 19th and early 20th centuries saw the development of larger, more powerful telescopes. These allowed astronomers to see further into space and to discover new celestial bodies, such as Neptune. However, these ground-based telescopes had limitations, mainly due to atmospheric interference and light pollution. The launch of the Hubble Space Telescope in 1990 marked a significant leap forward. Positioned above Earth's atmosphere, Hubble provided clearer, deeper views of the universe than ever before. Its observations have led to breakthroughs in how we interpret dark matter, the age of the universe, and the evolution of space. Following Hubble, other space telescopes, including the Chandra X-ray Observatory and the Spitzer Space Telescope, have observed the universe from space. In addition to optical telescopes, radio, infrared, and X-ray observatories have expanded our cosmic toolkit. These instruments allow astronomers to detect and study phenomena such as the universe's microwave background radiation, star formation regions, and the remnants of supernova explosions. Dark matter remains one of the universe's biggest mysteries. Invisible yet comprising a significant portion of a galaxy's mass, dark matter does not emit, absorb, or reflect light, making it invisible by conventional means. Instead, its existence is inferred from gravitational effects on visible matter, radiation, and the large-scale structure of the universe. In Andromeda, evidence for dark matter comes from the galaxy's rotational speed. Stars near the galaxy's edge rotate at similar speeds to those near the center, contrary to what would be expected if only visible matter were present. This uniform rotation rate suggests a significant amount of unseen mass attributed to dark matter enveloping and influencing the galaxy. Observations of Andromeda also reveal a massive halo of dark matter extending far beyond the visible stars. This halo affects the motion of satellite galaxies and star clusters orbiting Andromeda. By focusing on these orbital motions, astronomers can estimate the mass and distribution of dark matter within the galaxy. Such studies indicate that Andromeda's dark matter halo is both massive and extensive, extending north of 1 million light-years from its center. The distribution of dark matter in Andromeda is not uniform. It is denser near the galaxy's center and becomes less dense outward. This distribution affects the formation and evolution of stars and gas clouds within the galaxy. Dark matter's gravitational pull helps shape the spiral arms and influences the rate and location of new star formation. Additionally, dark matter is believed to play a significant role in cosmic collisions and mergers. The expected collision between Andromeda and the Milky Way, for instance, is also a product of the vast dark matter halos surrounding the two galaxies. The dynamics of this collision, including the eventual state of the merged galaxy, will be significantly influenced by dark matter. The new discoveries from the Andromeda Galaxy have significant implications for how we interpret the universe. Andromeda's findings provide crucial data on galaxy formation and evolution. By observing Andromeda's structure, astronomers gain insights into how galaxies develop over billions of years. This includes the formation of spiral arms, the growth of central bulges, and the role of collisions and mergers in shaping galaxies. Understanding these processes in Andromeda helps astronomers develop more accurate models of cosmic evolution. Across the universe, Andromeda's findings contribute to the refinement of space's distance ladder. By measuring distances within Andromeda and comparing them with those from other galaxies, astronomers refine the methods used to determine cosmic scales. This is crucial for estimating the expansion rate of the universe, a fundamental parameter in cosmology known as the Hubble constant. Additionally, the study of Andromeda's stellar population and chemical composition offers insights into the life cycles of stars and the distribution of elements across the universe. These findings help astronomers understand the processes of nucleosynthesis and chemical enrichment that occurred in the early universe and continue to occur within galaxies. Space exploration, while advancing our knowledge and technology, presents environmental challenges. The launch of rockets, for example, releases pollutants into Earth's atmosphere. Rocket fuels emit chemicals like chlorine and alumina, which can harm the ozone layer and contribute to atmospheric pollution. Debris is another significant issue. Space missions leave behind debris or space junk, ranging from spent rocket stages to broken satellites. This debris orbits the Earth at high speeds, posing collision risks to operational spacecraft and satellites. Efforts to track and remove space debris are ongoing, but the growing number of objects in space makes this a complex environmental challenge. On planetary surfaces, contamination is a concern. Rockets visiting other planets or moons can carry Earth-borne microorganisms, risking the contamination of these environments. This is particularly crucial in the search for life, as introducing Earth life can complicate the detection of native organisms. Space missions must adhere to planetary protection guidelines to minimize this risk, ensuring spacecraft are sterilized and missions are carefully designed to avoid environmental contamination. Light pollution is an often overlooked consequence of space activities. Satellites and large star clusters, like those used for global internet coverage, reflect sunlight back to Earth, impeding astronomical observations and altering the natural. In conclusion, the study of the Andromeda Galaxy offers valuable insights into the universe's structure, evolution, and future. By comparing Andromeda to the Milky Way, astronomers gain a better understanding of galaxy dynamics. Observing Andromeda's characteristics, such as its spiral arms and supermassive black hole activity, provides a reference point for studying similar features within the Milky Way. This comparative approach refines our models of cosmic dynamics and evolution. Moreover, the discovery of Andromeda's size and mass challenges previous assumptions and reshapes our perspective on the Milky Way's place in the local group of galaxies. Understanding Andromeda's evolution provides clues about the events that lead to significant changes in galaxy morphology. By simulating Andromeda's current status and predicting its future trajectory, astronomers can anticipate the effects on the Milky Way and refine models of cosmic evolution. However, space exploration also presents environmental challenges, including pollution and contamination, which must be addressed to ensure the responsible exploration and preservation of space.